Hey there! Before we dive in, just a quick favour to ask. If you're enjoying the show, don't be shellfish. Please take a moment to rate and review it wherever you're listening. It helps more people find us in the big blue ocean of podcasts. You can also support us by hitting that follow or subscribe button, following us on Instagram at Word on the Reef Podcast, and sharing the podcast link with a friend who might love it too. And if you'd like to help keep us afloat, please consider becoming a patron for as little as $5 a month over at patreon.com/wordonthereefpodcast. You'll get a shout out on the show, and your support helps cover the behind the scenes costs like hosting, editing software, and more. Thanks so much. Now let's get into today's episode. You're listening to Word on the Reef, diving into marine science on the Great Barrier Reef and beyond, with Tanya Murphy and Brett Goodban. Good morning, everyone, and welcome to Word on the Reef. I'm your host, diver and marine conservationist Tanya Murphy, and with me, as always, is Cairns Aquarium's marine educator and fish whisperer, Brett Goodban.
Good morning. Gee, that week went quick, didn't it?
It was, and it was a very stormy week, as we just talked about on the weather. And so I understand you've used up another one of your 9 lives in the stormy weather.
I don't know where I'm getting them from, Tanya. I really don't.
How many do you possibly have left?
Oh, crikey. Hopefully I've got a few more. Yeah, I was standing at the kitchen looking out the window during that big storm on Sunday, and me and my little fella were looking out the window, and 3 lightning bolts just landed on the driveway just in front of us on the other side of the kitchen window. His hair stayed on end. Mine didn't, because I don't have any. Frightened the life out of us. That was a big storm.
I'm really glad that you weren't going to the letterbox at that point in time.
Oh, gee, you're going for a swim.
Yeah, and I understand it's not the first time you've been metres away from a lightning strike.
Yeah, look, just as a community announcement to anyone in Cairns that's thinking about it, might be a good idea to wash their car and then wait for the rain to turn up and then do a lap of the beach so it washes it off. I got as far as the end of the driveway and a lightning bolt hit the tree to my left, and I just put it in reverse and parked it again. Yeah, I'm not going to do that today.
Yeah, you're like, actually...
I thought it was the best plan ever. If I just chuck soap on it, let the rain wash it off, beautiful. Nah. No.
Okay, so Brett, have you ever seen or done that fun experiment where you place an egg into a cup of vinegar?
Oh, no, I haven't actually. No.
Only me? Okay.
It's only you.
So maybe some listeners might have seen this on a video and might know what happens. But what happens in that experiment is that the acidity in the vinegar will actually dissolve the calcium carbonate eggshell. So you end up with a squishy egg that just has a soft skin.
We're talking pre-boiled or boiled?
No, just a raw egg.
Just a raw egg?
Yeah.
So what happens to it when the shell goes?
Well, it just has a skin around it instead of a hard shell.
I know what I'm doing this afternoon.
So what this experiment teaches us is that when something is acidic, it dissolves calcium carbonate, which is what eggshells are made from. So Do you know what else is made from calcium carbonate?
Oh, our Great Barrier Reef.
Coral,
our beautiful coral.
And the shells of molluscs as well, crustaceans, sea urchins, starfish, and some types of plankton. That is why scientists, oyster farmers, prawn fishers, and just about everyone else on the planet is, or should be, very concerned about increasing ocean acidification.
Yes.
Of the 9 planetary boundaries considered crucial for human survival, ocean acidification is one of 7 which have recently been crossed. But what's driving ocean acidification? How is it impacting our Great Barrier Reef? And what can we do about it? To answer these burning questions, our guest today is Dr Katharina Fabricius from the Australian Institute of Marine Science, or AIMS. Dr Fabricius is an international leader in coral reef ecology and a global expert on ocean acidification's impact on coral reefs. She has published more than 200 journal articles, book chapters and books, which have been cited more than 32,000 times in other scientific studies. Her research has informed policies, regulations and environmental solutions for many organisations, including the United Nations, OECD and World Bank. Good morning, Dr Fabricius. Welcome to Word on the Reef.
Thanks a lot. Good morning, Tanya and Brett.
Good morning. Thank you so much for joining us. This is going to be a great chat today.
Great to have you on the show. Now, I understand you live on Magnetic Island. Lucky you.
Yes.
We did an entire show about Maggie Island back at the start of last year with underwater photographer Lawrence Skill. Sounds like, well, I've been there. It is an incredible place.
Yeah, I love Maggie.
What's it like there today?
Right now it's a little bit wet. We've got a really heavy rainfall, so I'm a bit flooded in, but it's a beautiful place.
Yes, absolutely. I mean, watch out for the lightning.
Yeah,
but
please be careful of lightning, okay? You'll be fine if I'm not near you.
Yeah, Brett attracts the lightning.
Yeah,
it's his
apparently.
energy levels that
There
attracts it. So, Dr. Fabricius, I understand you're originally from Germany. How did you come to be so passionate about coral reefs?
Oh, who can't love coral reefs? I mean, they're really, really amazing ecosystems. But for myself, I knew I wanted to become a biologist from early on. And it was during my university times that I heard about AIMS and the cool things that they're doing. And it was sort of a light bulb moment. I sort of suddenly realized what I really want to do with my life. I was 24.
How old?
So, initially 22 when I heard about it first. And I went and saved up some money and then came over to Australia first in 1988. I was about 24 years old.
Wow.
And then I did an internship at AIMS, and I guess the rest is history.
Yeah, so you've been there for 37 years now, and you know you've found your perfect ideal job when you find it almost straight out of university and you stay there for 37 years. What a great achievement.
Yes.
So I believe congratulations are in order, because just last week you were awarded the 2025 AIMS Medal alongside your colleague Libby Evans-Illich for your sustained contributions to AIMS over many years. So
Wow, congratulations.
well done. Do you have still a few years left in you?
I very much hope so. Still totally love what I'm doing, and I've got a great team, a great place to work, great students, and look, there's so much important research to do. And coral reefs are incredibly complex systems, and I still keep learning stuff every day. So I hope I'll be around for a little longer.
We hope so too.
Yeah, and I think that's the key though, isn't it? You know, if you're in a job that you love, you're just open to learning as much as you can every day. Just being open-minded.
Yeah. And corals are really complex organisms, so they keep surprising us on a daily basis.
Yes, cheeky little buggers.
Yes, for something that's built from creatures so small, they continue to puzzle us. Now, I understand you are frequently seen in a wetsuit rather than a lab coat. How much time do you spend out there on the reef?
Yeah, I love being out there, and I think it's really essential for anyone studying coral reefs to get the natural history and to be out there and to observe rather than just using abstract models and sitting on my desk. Unfortunately, a little bit less than my early years, but still probably about 30 days or so per year. So we've just come back from a field trip off Cairns, and we're going out again in early March.
Beautiful. Now, I understand you have a bit of a soft spot for soft corals.
There you go. There's our pun for today.
What do you love about soft corals, Dr. Fabricius?
Well, first of all, soft corals are incredibly pretty. So whoever has been out on the reef and sees these colorful dots or fans or rods or rust or so, that's a soft coral. And there are a lot of them out there on the reef, so they're really the second most common organism next to hard coral. And it was literally nothing known about them when I started in the 1980s. So I learned more and more about them and became more and more fascinated by their complexity and their nature and their biology.
Yeah, a lot of people, when we take them snorkeling and you point out soft corals like spaghetti corals, they think it's either seaweed swaying in the current or an anemone because it's so soft and squishy. But there's a whole category of corals which are actually soft. Like you said, the fans, whips, and various other different types of soft corals. What are some of the most interesting things you've learned about soft corals throughout your research?
Well, first of all, we didn't know anything about them, so not how fast they're growing, what they're doing, who eats them, and so on. So I started off looking at whether soft corals take over the space when conifon starfish eat the hard corals, and found that it's not the case. Yeah, just really sitting there and leaving the space open for the hard corals to come back.
Well, that's very polite of them.
Isn't that cool?
Yeah.
No, after you. You go first.
Yeah. No, it's really intriguing. And what I found out is that soft corals and hard corals really occupy what we call different ecology niches. That's because soft corals are feeding on what we call phytoplankton. These are these tiny algae that float in the water. So they're vegetarians. Whereas the hard corals, they're carnivorous. They feed on zooplankton. So they're really not competing against each other in terms of nutrition. And soft corals are also not quite as fast. They're sensitive little critters. They need a lot of currents, not a lot of disturbances in order to be happy.
Right, so it's not really good for them to be wanting to move into that area that the crown of thorns ate, because it's not really somewhere he wants to be, right?
Yeah, I mean, in some cases, they're just too slow to take advantage of it.
Yeah.
Hard corals can be quite weedy and can be very fast in recovering if the environment is good and water quality is good and so on.
Is it something that the crown of thorns leaves behind afterwards that's sort of making the soft corals go, no, we don't want to borrow that?
Yeah, to some extent. I mean, soft corals are full of feeding deterrent chemicals, and the coral thorns are really specialized in feeding on hard corals.
Yeah.
And they've got to be really hungry and desperate before they take a nibble.
Yeah.
Soft corals.
That's what I understand about soft corals, because they don't have as hard of a limestone skeleton to protect themselves. They rely on tasting really yucky. But
Crown of thorns are fussy.
as you said before, you were drawn to studying soft corals because they're so pretty. Well, that's one of the things that I love about them as well. But in the course of studying soft corals, what did you discover about how they are impacted by water turbidity and sedimentation, as in stirred up and polluted water?
Yeah, I mean, water quality is an issue for a lot of different reef organisms. But since I happen to study soft corals, I looked at how soft corals and sea ferns are responding to sedimentation and greater turbidity, and I found that they're really highly sensitive to poor water quality. So the greater exposure to terrestrial runoff of sediments and nutrients, the fewer types of soft coral you find, the fewer species there are. So the biodiversity is really going down, and the density of many of the groups is going down as well in areas where there is a lot of sedimentation and the water's not so clear.
Well, that's unfortunate. We don't want to lose our beautiful...
No.
Too many of our beautiful soft corals. Now, you live at Magnetic Island, which is very close to the dredging carried out by the Port of Townsville to maintain that shipping passage into the Townsville harbour. Has your research revealed anything about the impacts of dredging on coral reefs?
Good question. It's not an area I've worked on, and it's very difficult to separate out the direct impacts of dredging. So direct dredging is probably relatively short-lived. But then we are also seeing the impacts of the resuspension of the fine, blocky dredge spoil from ongoing maintenance dredging. So it's complicated. This maintenance dredge spoil is placed in very shallow waters, and that in an area where it's really easily resuspended, and that's upstream of Magnetic Island. But it's really complicated because Maggie is also very close to the huge Burdekin River that discharges, on average, I think it's 17 million tons of sediment per year on average. It's mind-boggling.
Yeah, I think it's one of the biggest outputs of water of any river in the world. Maybe it was what one of the previous guests told us, or it was one of the Queensland rivers anyway.
It's the biggest one in Queensland by a country mile, and it's one of the bigger ones. Not quite beating the Amazon or the Fly River or so, but we're up there.
Yes.
Yeah.
So that sediment, we've talked about it on a couple of previous shows, talking extensively about how humans removing vegetation, clearing forests, especially along those rivers and creeks, is increasing the erosion of sediment into the rivers, and that's obviously having an impact on the reef. So we've had a few episodes about that, and then there's other human activities like agriculture and industry and so on. But we've talked about that in some other shows, and we want to talk today mostly with you about ocean acidification, a problem affecting our oceans in a way that has scientists quite concerned. So, Dr. Fabricius, what is ocean acidification?
We call it the second sin of climate change, or the twin of climate change. We obviously have warming, but if we've got more CO2 in the atmosphere, that CO2 is absorbed by the seawater to some extent. And the word acidification means that things get a little bit more acidic, like when you sort of add vinegar to water, it becomes more acidic. And similarly, if you dissolve bicarbonate in water, it becomes more alkaline. So seawater is slightly alkaline and will always remain alkaline, never going to be acidic. But the word acidification means it's slightly getting less alkaline.
Mm-hmm. So the pH is increasing?
Declining.
Declining, sorry.
Well, it's a 50-50 chance there.
Back to year 9 science for me. Okay, so the pH is declining, it's becoming less alkaline, and as I was joking to Brett earlier, what we like to have is basic beaches, not acidic beaches. He didn't really get it.
A little bit of hidden science joke. It was too late for me.
So what is causing this ocean acidification?
Okay, ocean acidification is purely a consequence of our human-induced CO2 emissions. So seawater and air are in equilibrium, and it's like our beer is getting flat when we have it sitting on our bench for too long. That CO2 from the beer is getting into the air. Mm-hmm. And similarly, if there are high levels of CO2 in the air, it goes into the ocean. And the rest is pure chemistry and physics. Higher CO2 in the ocean forms something we call carbonic acid. So it's this very mild acid, but nevertheless, it does reduce the pH in the seawater.
You know you're German when you're using beer to explain science.
I love that.
But I was thinking about carbonated beverages like even just soda water or Coca-Cola. You can see the bubbles of carbonate.
Oh, no, I'd already gone for a pint of Great Northern. I was with Doctor then, for sure.
Yes, and that's why drinking those fizzy drinks can rot our teeth. It's not only the sugar, but also the acidity that rots our teeth. But now we've got a problem in the ocean akin to that. How much more acidic is the ocean around Australia and the world now compared to pre-industrial times?
So there's some regional variability, but on average, the surface waters around Australia are now about 40% more acidic than since the 19th century.
40%?
Wow.
Yeah, 40%. And because CO2 is a nutrient for plants and so on, that really means it's a massive change in all aspects of the seawater chemistry.
Yeah, so as you mentioned, humans are burning fossil fuels like coal, oil and gas. It's releasing CO2, carbon pollution, into the atmosphere. It's getting absorbed into the ocean. And now the ocean is 40% more acidic in just the last sort of 200 years. But the level of carbon dioxide in our oceans has varied throughout ancient prehistory. How do we know that what's happening now is not a natural cycle that marine organisms can adapt to?
Yeah, a good question. What we're really concerned about is the rate of change. So the oceans around Australia are acidifying about 10 times faster than at any point in the last 300 million years.
300 million years, wow.
Yeah. That's enormous. And it is accelerating. I mean, pH is the measure of acidity. So far, it's only dropped from 8.1 to 8. That doesn't sound like much, but it's on a logarithmic scale. So it's really massive increase in acidity and accelerating.
Yeah.
So that's really too fast to adapt. And so I'm really concerned about it because it's a global issue. It's not just a local issue.
Let's talk about sea creatures. How do sea creatures like corals and molluscs create their calcium carbonate shells and skeletons?
So that really would need a deep dive into physiology. It's like humans grow bones through calcium we eat, from milk and so on. Marine organisms take all the need from the seawater. And if you add CO2 to the seawater and you form this mild carbonic acid, what happens is that the whole carbonate chemistry goes wonky. You're reducing the amount of carbonate, and the calcium and magnesium is there in abundance, but what is becoming limiting is the carbonate to form those shells. The organisms are pretty clever that you use proton pumps to create suitable conditions between the tissue and their skeletons, but that takes a lot of energy to pump out those protons, and so in result, the organisms find it more difficult to calcify.
Right.
Just another way we're making life harder for them. So relevant to this are some research expeditions you did in Papua New Guinea, which sound like they must have been incredible trips. Tell us about those research expeditions.
Yeah, it started off with again, back to soft corals. So I was invited by an actually Australian tour operator to join one of his expeditions to Papua New Guinea to do surveys on soft corals and sea fans.
Who was that?
Rob van Boosik, the Churchin.
I thought it might have been someone I'd heard of, but no. Anyway, sorry to interrupt.
Yeah. Anyhow, PNG has got really amazing coral reefs. It's incredibly diverse.
Yeah, it's
really
beautiful over there.
ways. A lot of colour, a lot of fish. And it's an amazing place to dive. Yeah, and when I was diving there, I saw these bubbles emerging out of the seafloor. And at that time, ocean acidification was absolutely not on my horizon, and really not on the horizon of most researchers. But later on, I started working on the topic in the lab, and I was sort of trying to bubble the CO2 into the seawater to stimulate ocean acidification. And while I was doing it, I remembered that I'd seen these large areas of gas bubbles coming out of the seafloor in Papua New Guinea. And Rob van Boosik was kind enough to go out and collect those gas bottles for me, and turned out to be pure CO2. So I was just amazingly lucky. And it was again a Cairns photographer who helped me doing the whole thing as well. But Roger Steen, who is a really, really great photographer in Cairns, underwater photographer.
Who's that, sorry?
Roger Steen.
Oh, okay.
Yeah, great person. And yeah, anyhow, once we found out that it's pure CO2 and no other pollutants in these gases, I knew I had sort of a natural laboratory to study the responses of coral reefs to local ocean acidification. I mean, it's sort of simulated because CO2 is coming from volcanoes, not from the air.
Yeah.
But it allowed me to use it sort of like a time machine to look into the future, how whole reef organisms at natural flow, at natural light and so on respond to ocean acidification.
Wow, what a great study. And underwater volcanoes too, that's pretty cool.
There's so much interesting about this. Like, firstly, you were just going for a dive and you noticed bubbles coming out of the seafloor, like you're swimming in a Coca-Cola, and you're thinking, what are these?
Or a Heineken.
And then you asked someone to get some samples and you found out that they were pure CO2, but they're coming from underwater volcanic activity. How acidic are these carbon dioxide seeps that are seeping out of the ocean floor in Papua New Guinea?
Yeah, so we basically use these like time machines because there are areas of low bubbling and there are areas of no bubbling, which we could use as control areas. And the more intense the bubbling was, the lower the pH went. So in some areas it went as low as 7.5, which is hopefully something we will never experience in the worst climate scenarios. But there are extensive areas of about 7.8, 7.7. The conditions we are predicting to occur towards the end of the century, in particular if our emissions don't reduce.
Which is the condition we're expecting by the end of the century if we don't reduce our emissions?
About 7.8 to 7.7, unfortunately.
Jeepers.
Okay, so you use
170% increase in acidity by 2100.
Oh.
170%. Okay, so we're at 40% more acidic than pre-industrial times now, and expecting 170% by the end of the century at current emissions rates, which is a drop from about 8.1 down to 7.8. 7.8. So it doesn't sound like that much of a drop, but as you explained earlier, it is a curve and it's accelerating. So like you said, that's a concerning look into the potential future. So what did you see in terms of how these different levels of acidity were impacting the marine life?
Yeah, the interesting thing is the more CO2 there is, the lower the reef diversity is. Coral cover did not change all that much, but we were losing all the branching and tabulate and structural corals.
So all your staghorns and plates.
Yeah. And they were replaced by massive boulder corals, we call them parietes, which is, I mean, they're great corals, but they're not good habitat for the shrimps and starfish and fish and whatever is living on coral reefs because they don't provide that shelter.
Yeah. No offense to boulder corals. Some of my best friends are boulder corals, but they can't, they don't have this structure.
We still love you, boulder corals, but you're not a very good apartment block for all the critters.
Boulder corals are people too, but that diversity loss that you're talking about is so concerning.
Loss of diversity, loss of capacity for reefs to recover, more algae because there's more CO2. And what's really missing is what we call crustals, coralline algae. They're these beautiful pink crusts that are all over the coral reefs. And little coral larvae need them to settle. So little larvae like pink, like little girls. And so these coralline algae are incredibly sensitive to acidification, more than anything else, really, almost. And if they're missing, then you don't get enough coral recruits, the coral babies, and therefore the rate of recovery is declining. And similar for foraminifera, like the stuff that's building Rain Island and many of our beautiful coral caves, they're mostly made out of single-celled little chips that are called foraminifera.
Yes, I remember learning about them on our Rain Island episode, foraminifera.
Foraminifera, and they're incredibly sensitive too, which is bad for our turtles again. So everything's connected.
So not only...
Sea urchins were actually winners. We thought sea urchins have calcium carbonate shells. They should be really pissed off about the CO2. But because there's so much algae around, that they've got more food and therefore they've got more energy and therefore they're actually doing better in high CO2 areas.
How fascinating. So the urchins are like, we're willing to tolerate this acidic environment because there's so many plants that we can eat here. How interesting.
Yeah. And similarly, crustaceans, which we again thought they were fairly robust because they run around and they produce CO2 in the body and they've got all the mechanisms to excrete the CO2, but they were almost missing in the high CO2 areas because their habitat was missing because they like to be sheltered in those branching corals.
Yes.
They get eaten by fish.
Yep.
So we saw all these things which you can't actually really simulate in laboratory experiments, those flow-on effects on these incredibly complex ecosystems. And that shows how important it is and how massive these impacts are because, there are all these flow-on effects too.
So our poor old corals dealing with the ocean turning into soup, and now they've got ocean acidification rising as well. It's a bit of a battle, isn't it?
It's getting hotter and it's getting more acidic. And it was really interesting what you told us, Dr. Fabricius, that coralline algae is this pink sort of like cement that covers things over and forms a really good base for baby corals to land on and grow. And that pink coralline algae is being dissolved by high acidity in the seeps where you researched it. So there won't be as many or maybe any safe places for baby corals to grow in future. So that was a really interesting point that I learned in the last 2 minutes from listening to you. And it's interesting to hear about which species will be the so-called winners, the older corals, more capable of living in acidic environments, and which ones are the losers, in inverted quotes, the more fragile branching corals and plate corals, which are just absolute favourites of everyone.
And losing those as well is tough because they're obviously the fastest growing ones. There's more abundance of those. So providing that shelter and that food for all the critters, that's going to be tough.
Yeah, and they're just incredibly pretty to look at.
Yep.
What impact is there on soft corals, your favourite type of coral, Dr. Fabricius?
That's an area we don't know a lot about because they've got a lot of really thick tissue and very little carbonate structure. So I'm hoping they'll be a little bit less affected, but we really don't know.
Our guest today is Dr. Katharina Fabricius, coral reef ecologist with the Australian Institute of Marine Science and an international leader and global expert on ocean acidification's impact on coral reefs. And Dr. Fabricius has been diving in Papua New Guinea, discovered carbon dioxide bubbles seeping out of a volcanic seep, and that was creating a small microcosm of ocean acidification at really high levels. Was able to study the impacts on the marine life, which gives us a world first, I suppose, peek into what oceans might be like in future if ocean acidification from human carbon emissions continues. So I'm not aware of there being any carbon dioxide bubbles seeping out of the ocean floor on the Great Barrier Reef, but the entire ocean is now 40% more acidic than pre-industrial times due to humans burning fossil fuels and releasing carbon dioxide into the atmosphere. So, Dr. Fabricius, do we know what impact that's currently having on marine life on the Great Barrier Reef, given that the ocean is 40% more acidic?
Yes, so the Great Barrier Reef is huge, but what we've found from existing long-term monitoring and survey data is pretty much parallel to what we found in Papua New Guinea. There is fewer of these crustose pink coralline algae, there's more macroalgae, and there's fewer coral juveniles in areas that there are a little bit lower pH levels. As I said before, there are some regional differences, and in particular in the Great Barrier Reef, in particular through higher nutrient levels inshore, we get what we are calling coastal acidification as well. So there's more respiration, there's more CO2. And so in areas where the pH is slightly more acidic, we are getting fewer of those coralline algae, more macroalgae.
Right.
So that's another thing that affects inshore reefs more than outer reefs, because it's also warmer usually in the shallow inshore where the water sort of pools up and gets exposed to more heat from the sun. But it's also the acidification is pooling up near the coast. But did you say it's also because there's more emissions, I guess, local to the shore areas where humans live, I suppose?
Oh, the emissions are pretty much mixed throughout the globe, but it's also a matter of, as you said, temperature, and there are latitudinal gradients, and it's a matter of what the reef and the benthos does to the seawater. Okay. So it's dynamic. There is, even between day and night, there are differences because the organisms are breathing at night and doing photosynthesis during the day and so on. But overall, if you average it out in areas of lower pH, higher acidity, you find more algae, fewer corals recovering, fewer types of corals, and therefore slower recovery from...
And just a reminder to any of our international guests that haven't been over here yet, just a reminder the reef is massive. 2,300 kilometres, 3,000 reefs. She tapers in, she tapers out. Some are out in the deep, some are inshore. So, yeah, some areas are affected more by this than others. So what area would you say would be affected more? Would it be like coastal inner reefs around Cairns, Mission Beach, areas like that?
Most of the offshore reefs are in pretty good condition.
Yep.
And most of the areas further north are in really good condition. So a colleague of mine did a really clever experiment. She released a little bit more alkaline chemistry upstream of a coral reef, and then to an extent restored the conditions that would have happened pre-industrial times. And she measured how much the reef calcification is increasing. So there was a nice way to show how much the situation is already impacted by ocean acidification, that much that has happened today. So
throwing...
You can only do it at a really local scale, but it's just a demonstration of how much slower the reef is growing in areas where acidification is increasing.
All right, so listeners, what we need everyone to do is to run down to the beach and throw your antacids into the ocean.
Yes, just buckets of Mylanta, please.
We're just joking, of course. It's a slightly bigger, much bigger problem than that. Obviously, we can't all go and throw antacids into the ocean to solve this problem. What is the solution to ocean acidification, Dr. Fabricius?
Well, the only solution really is to stop carbon dioxide emissions. We don't have the technology to fix it. It's a global issue. And there's no latitudinal escape. Like for warming, at least if conditions are good, some organisms can do what we call poleward migration. They can get away from the really hot areas and going into higher latitudes. But with CO2, you can't do it. It's global. It's everywhere. And the ocean is so vast. Some people are talking geoengineering and stuff, but at this stage, we don't have any technologies to fix it, and I don't believe there will be quick technologies to suck the CO2 out of the oceans if it is in the atmosphere, because the only way to do it is take it out of the atmosphere.
Yeah, we do. We urgently need to stop burning fossil fuels and releasing all that carbon pollution into the atmosphere. It's both because of the heat that it's causing and also because of ocean acidification. I've seen articles about more acidic water impacting fish behaviour as well. Have you studied anything on that? Or maybe that's a topic for another episode if it's a really big one.
Yeah.
Yeah, and that's a colleague of mine who's worked on it, or a number of colleagues, and it again shows how really poorly understood ocean acidification is. Very few people are working on it, and for a little while there was a bit of a flurry of activity, and now it's declined again because the warming has been really sort of pushed into the foreground because the temperature, the heat waves causing such massive visible damage to coral reefs that ocean acidification is sort of this creepy threat in the background.
Yeah, and I guess there's also the effects of coral spawning too with ocean acidification. That's probably something else to look at quite seriously as well, isn't it? Whether that's affected or not.
Yes, and again, we don't really know. There's a lot of issues. Yeah, like fish behavior, they found that fish are not recognizing their predators any longer.
So they're on acid and they're swimming straight into the shark's mouth.
Don't. They thought the shark was a unicorn. Fish.
Like, hello, yes, I would like to come for dinner.
Oh, you didn't do that to my brain. I've drifted off.
We have to make light of it, folks, because otherwise we'll just cry. Now,
I can't imagine Chang on acid, to be honest.
We don't have much time left. I just want to reel through some of the other impacts though, because it's not often we talk about acidification. There's so much to say about it. I've read that ocean acidification will continue breaking down the limestone that coral reefs have laid down even after they're dead. So it will reduce the shore protection from storm surges and tsunamis, etc. Do you have anything to add to that, Dr. Fabricius? Have I got that summed up correctly?
That's totally correct, yes. Again, boulder corals may contribute to shore protection as well, but we need really healthy ecosystems that are in equilibrium, not just massive boulders, massive boulders.
Diversity.
Because massive boulders are also growing quite slowly and sea level rise is accelerating. So, yes, it is a huge issue for climate change in general.
Yeah, I think I read a statistic up to 97% of the force of hurricanes and cyclones can be absorbed by the coral reefs along the shore, reducing those wave surges. So we're going to be looking down the barrel of more extreme disasters like that, not only from the heating of the planet, but also because those coral reefs won't be there to protect us. The impacts on fisheries. So I was reading about, I didn't see any articles about Australian oyster farmers, but I read that aquaculture oyster farmers in the USA, as early as 18 years ago, started losing their oyster larvae in mass die-offs, threatening a huge part of the economy. And it turned out they've discovered it was the acidification of the seawater that is circulated through the aquaculture ponds. So they've started having to put sodium carbonate into their aquaculture ponds, but without further mitigation, it's going to have a significant impact on our fisheries, our aquaculture, and on consumers. Do you have anything to add to that, Dr. Fabricius?
No, that's exactly right. And again, it shows the complexity of the issue. And literally 500 million people globally depend on coral reefs. So in each area, they depend on coral reefs to different extents. Some is tourism income, some is just the protein. If the corals are missing, the fish are missing, and the protein's not there, and so on. So it's really complex. But in general, unfortunately, the news is in no way positive.
So we talked about the solution is obviously to stop pumping new carbon dioxide emissions into the atmosphere. That means we shouldn't be approving any new fossil fuel projects, and we should be investing in renewable energies as quickly as possible. And we should all be using our voices to ask our world leaders for those sorts of policies. But while we work to get emissions under control, are there any local adaptation measures that can help corals and marine life to adapt to acidification?
Presently, we don't know of any. So a lot of scientists are sort of trying to work solutions to breed more heat-tolerant corals, but the temperature, because of the bleaching effect, is so dominant at this stage. We haven't had really the time to look at more acidity-tolerant corals. And if you look back in the geological past, there have been areas of high CO2. And in all cases, there's a gap in the fossil record of coral reefs that lasted 1 to several million years. So even in the geological past, when impacts were not quite as quick, corals did not show any sign of being able to deal with more acidic conditions.
Yeah, so when you say there's a gap in the fossil record, you mean that basically the majority of corals on the planet have gone extinct when CO2 levels reached these levels in the past, or, well, like you said, they weren't even as high as they are now and they didn't happen as quickly, and yet they caused mass extinction of corals in the past, from which it took millions of years for corals to sort of recover back. So, like you said, there's not really anywhere corals can move to escape from acidification because it's in the whole ocean. So, well, some people are putting their hopes in coral refugia, which are areas that might be a bit cooler. Unfortunately, there won't be any safe places where corals and marine life can go to get away from the chemistry of the ocean, which is acidic everywhere, which really all just highlights how important it is for everyone in the world to be talking about this, spreading the word, talking to your leaders as urgently as possible, because we can't just be putting our hopes in short-term actions.
That's right.
Like breeding those heat-tolerant corals. We really need to prioritise cutting the emissions.
And also local activities. Like if we have more algae because of CO2, we need to manage fisheries to sort of give the herbivorous fish a good chance. We need to improve water quality because of the interactions between CO2 and water quality and so on. The local conservation actions are becoming more important than ever.
Yeah, that's true. So we do have some things that are very squarely in our own power, like stopping tree clearing, planting more vegetation in ocean catchments, managing fisheries. All those other local actions can make things a little bit easier on the marine life while they deal with those stressful conditions.
And the important thing to remember also is that we can't keep forgetting that we are an ocean planet. Everything that happens to our ocean will affect us. 70% of us is ocean. It's important that we have shows like this and amazing scientists like yourself and, people spreading this word and giving people the correct information. It's all up to us. It's all up to us to change this.
We've spent a lot of time on this show talking about hope and the fact that we can all make a difference. So although today's topic is a serious one, I hope all the listeners will heed our frequent message that if we all get together, there is something we can do about this and we can make a difference.
Yep.
But Dr. Fabricius, when you started working on the reef 37 years ago, I bet you didn't predict that within your lifetime you were going to be fighting to try and save it, or at least certain species of it, from extinction. Do you experience ecological grief from the changes you're seeing in coral reefs, and how do you handle it?
I do, and a lot of my colleagues do as well. So it started with a back-to-back mass bleaching in 2016, 2017. And, since then, it took me a while to get over it, to recover. And I think a lot of us are now trying to work on solution, not just describe how bad it is, but so we've been working through the reef restoration and adaptation program, trying to learn how to repair reefs, to scale up being able to repair reefs, because at this stage we can only do it at very, very, very small spots. We need to help reefs to get through the next decades. So my hope is that the world is coming to their senses. There will be a temperature overshoot, but hopefully towards the end of the century, then temperatures and ocean acidification will become milder. And so my idea is if we can help the reefs to get through the next few decades, and we've got some of the tools to do so, and others can be developed, then we hopefully can stand a chance to help reefs to recover and reflourish towards the end of next century.
There's projects of collecting coral species and keeping them in aquariums to hopefully replant them when conditions return to normal. But that's going to be a long time away, and we need to work really fast to get those emissions down if we want to have a chance to be able to plant those corals back into the ocean ever. So
well, remember that education leads to conservation, doesn't it? The more people understand and listen to this amazing show and incredible scientists in your field and everyone that knows what they're talking about, and not, as my old adage is, Kevin the plumber at the pub, like people that know what they're talking about. We can all chip in.
Yeah, absolutely. I wish we could talk for a lot longer.
Oh, yes.
But sadly, that's all we have time for today. Dr. Katharina Fabricius, coral reef ecologist with the Australian Institute of Marine Science.
Thank you so much for joining us.
Thanks a lot.
Do you have any last message to leave us on, or something that you'd like the listeners to take away, or something they can do? Or, just a takeaway message, Dr. Fabricius?
No, just what you just said. It's massively important that people learn as much as they can, go to trustworthy sources, like the Great Barrier Reef Marine Park Authority has got great websites, CSIRO, AIMS, reputable newspapers.
Unfortunately, our recording was cut off here by the 11 o'clock news, but Dr Fabricius concluded by urging us to get our information about climate change from reputable scientific sources, not blogs, social media posts, opinion pieces, conjecture, hearsay, Uncle Bill from the family barbecue, Kevin from the pub, or any source other than the scientific organisations who are doing the real, on-ground and in-water research on these issues. Which is why you've come to the right place here at Word on the Reef, where every week we interview the scientists at the forefront of marine research. A healthy coral reef is not a silent place, but rather it's like downtown New York, a three-dimensional metropolis, constantly bustling and alive with the sound of countless creatures munching and nibbling on coral, chirping and growling to warn off predators and attract mates, moving rocks around to build nests, and generally going about their lives. Here is some audio I took while freediving at Fitzroy Island on the Great Barrier Reef near Cairns recently. Today's episode reminded me that the death of a coral reef doesn't always look like a sudden, spectacular bleaching event that makes news headlines. Sometimes it's just a matter of the neighbourhood becoming gradually a quieter and lonelier place as old suburbs crumble and new ones aren't built in their place, causing the residents to gradually move away. In the course of a human lifetime, it might seem like a gradual change, but in geological time, it's happening in the blink of an eye. If this episode made you feel sadness, grief, or worry, you're not alone, and this is a totally normal response to what's happening. Please remember, lots of people are working on solutions, and you can be part of the solution too. Back in Season 2, Episode 11, we talked about meaningful actions you can take in your own life to help protect our oceans and tackle climate change together. In a few weeks' time, we'll be getting a psychologist on the show to talk us through some tips for handling ecological grief and anxiety. Until then, please take care of yourselves, and we'll be right here every week with more hope and solutions for our oceans.